And so he worked at the NASA Ames Research Center and for a number of years. And then he went to UC Berkeley, where he's been for 10 years or so. And he has a split appointment between civil engineering and the electrical and computer science, electrical engineering computer science department. And so most important for us is he's the new director of the Institute of Transportation Studies at UC Berkeley. And why I'm very excited that he's here is because Alex represents kind of the next generation of where a lot of the research and thinking in transportation is going and has to go. And that is, he works with sensors and all of the data that can be generated that way, and he's going to talk a lot more about it. But it is this idea that we have much easier way of getting data in the future and a lot more of it. And so some of you are already working in various aspects of so-called big data and so on. But I think this is an important, in working with the wireless technologies and the sensors. And so that's really going to become a very important part of transportation research in the future. So we're very delighted that we lured you here from the Bay, and thank you very much.
The clip fails. Okay. Well, thank you so much, Dan, for the invitation and for the very generous introduction. I'm really happy to be here. I was here a couple years ago in your older location. I think this is an absolutely phenomenal facility. I'm very jealous of you guys because our real estate is very expensive on campus, so it's hard to get a conference room when you guys get buildings. So today I'm not going to talk too much about ITS. ITS is, of course, a sister institute to your ITS, very broad spectrum. I'm mostly going to talk about things done in my own research group, and at the end, maybe expand a little bit to others. The title of the talk is Nash-Stackelberg Games in Transportation Networks, and that refers to some concepts that have emerged in behavioral economics and are really going to affect transportation in the era of the mobile internet. The general theme of the research I do at Berkeley has to do with large-scale infrastructure systems. The infrastructure has been revolutionized by the era of sensor networks about 15 to 20 years ago. And now it's been revolutionized again by a new era, which is the mobile sensing era and the social network era. As far as today's talk is considered, I'm going to mostly focus on transportation and expand that towards the end to other applications. When we think about classical sources of information for traffic, we're used to the old paradigm of the DOTs instrumenting their infrastructure with loop detectors, cameras, or wireless versions of these. That's the old paradigm. I think 60% or 40% of the loop detectors in California are failing every day, and this changes every day. They're extremely expensive to maintain. They only provide partial coverage. And then if you look at the arterial network, they're fragmented. So it's even worse because there's no single structure system to gather all of them. And if you think about the revolution of the mobile internet, this curve, which was given to us by Jim Sporer from IBM a couple of years back, is very telling. This is the number of devices produced as a function of time. You can recognize some of the old stuff, like some of us remember the Atari we used to play games with, or even the first Macintosh. That curve is quite telling. It's the Android curve. It's almost vertical. This is back in 2011, so now it's literally probably through the roof now. I mean, it's amazing because the number of devices produced per year was already in the millions. Now, this, in the context of transportation, has completely changed the way traffic information is provided. This 511 website from 2008 looks almost vintage, according to modern standard of design for the internet. This is standard to all of you because all of you have a smartphone and you have Google Maps or any kind of competitor product. And that provides you information on the arterial networks, which has virtually no infrastructure centralized to this day. This revolution happened within probably 18 months of 2008. And that's the first part of the talk I want to describe today. Berkeley had one of the very first prototype that was deployed in the US of this. And I think the interesting part is, the question is in the next decade, how will that play into traffic management and operations? So in the first part of the talk, and I apologize, the colors seem to be a bit weird, but when I refer to the red or the blue, if you don't see the colors, I don't see them either, so we're all equal here. I'm going to first talk about Mobile Millennium, which is the project that we created in 2008 to monitor traffic using GPS-enabled smartphones and try to show how the progression of the mobile internet has kind of steered the field of transportation engineering to an era it was really not supposed to be involved in. I mean, I think really the smartphone era has created a lot of connections. And then I'm going to dive deeper into one specific problem that we're working on today, which is the notion of games in transportation. That part will be way more mathematical, but I think is kind of where we think a collaborative traffic management is heading in the future. And then talk about a couple others here. So Mobile Millennium was the first traffic app ever deployed in North America to use GPS-enabled smartphones to gather traffic information running on RIM and Symbian phones. These names probably don't mean much to you today because they're gone. I mean, one of them was the BlackBerry, which was running the RIM system, and Symbian was the Nokia, which was the gigant of the year. Remember, in 2007, when we started this, the Android didn't even exist, and the GPS did not have and the iPhone did not have a GPS. So obviously, at the time, they were the platforms of the day, and this was what was at the disposal of engineers to monitor this, to monitor traffic. So we initially created that app, which had 5,000 downloads. At the time, that was enormous. Of course, nowadays, the scales have exploded. And we were able, by brokerage with several companies that already collected that data on dedicated fleets like trucks, to gather about 60 million data points for Northern California, mostly the Bay Area, some in Sacramento, to create this interface. Again, I'm sorry, the colors don't display very well on the screen, which was a first instantiation, if you will, of Google Map for traffic arterials. This was launched in February 2009. Couple days before Google launched its own arterial traffic features on the internet. And this was the phone of the time, which now looks also like a vintage collector's item. But this was very nice because this was a way for us to get a glimpse at the future of traffic monitoring. We also launched in Stockholm and several other cities in partnership with several companies. When we started this in 2008, it was not known at what percentage of penetration that thing would work. So if you ask the simple question of how many people need to carry a phone and transmit data to you for it to provide some reliable information, that answer was not known. In micro simulations, you could kind of guess that it was around 2 or 3%, but back in the days, nobody really knew. And the California DOT was extremely, and the federal DOT were very excited about figuring this out. And they kind of pushed us to kind of experiment beyond the simple proof of concept papers or even micro simulation and to do an experiment for real. So this is when this whole project started with the DRI at Caltrans. And so we did something very simple at the time, which is try to figure out what would it take to create 2% of traffic equipped with smartphones and show that you could reconstruct traffic in real time, at least as accurately as a dedicated system. So we hired about 200 Berkeley students, including 165 drivers. We give them a smartphone. At the time, it was an N95. That was a phenomenal phone for the time. And for 10 hours, we asked them to drive in loops, these 10 miles. So, of course, they took turns because of liability. And according to our computations, that created about 2 to 5% of traffic, depending on the period of time on the freeway. That's because we had a lot of cars, and they were rotating. It took about 20 minutes to do a loop. So if you multiply this by the number of vehicles and you get off the carpool lane, that's the number you get. So that number was magical because that number, at the time, was the forecast of traffic penetration of smartphones 18 months from the experiment. So your company like Nokia in 2007 or 8, you try to figure out in 18 months when the market grows, when I might have 2 to 5% of the population driving with my phones, is that going to be enough to provide traffic information? That was the research question they were asking back in 2007. So we were very happy because that worked. This is a couple pictures from, these are the old phones we were used at the time. We had a command center that was run from by former colonel of the Egyptian army. We needed someone with really good training in security to make sure that the students don't run out with the car and the phone and go somewhere with that. One did, actually. We had cameras and teams with cameras on the bridges. In fact, this is Chris. You saw him in Texas a couple of days ago. Actually, there's a funny story here. We had to do a lot of preparation with this, and we had teams with cameras on the bridges to validate our results, because you always want to have a validation set independent from your training set. And so a couple of days before the experiment, this guy, who is now a professor at UT Austin, who was an expert in physics, was selected, and he bought like 10 different video cameras to select a model that would work in rain, in fog, in sun, and in every possible condition, because we did not know what the traffic and the weather condition would be on the day of the experiment. And then he showed up a couple days before on the site and started filming the freeway at different times of the day and under rain and whatnot, just to make sure that we could re-extract the data regardless of the weather conditions. And inevitably, the California Highway Patrol got hundreds of phone calls that there's a strange guy with a hood on the bridge filming, and there might be some terrorist activities. So the police came really quickly and started yelling at him, "What are you doing?" And he showed them a California letter saying that's legit, and so on. And the police officer was very angry, and he told him, next time you go, you have to wear an orange vest and a helmet so people don't freak out. You can see the orange vest right there. He took the helmet off for the picture. So he continued doing it with the helmet and the vest, and nobody called anymore. So you can see if you want to do anything on a bridge, if you just wear the right equipment, they'll let you do whatever you want. So these are the bridges where we had posted the different teams, and they were basically recording everything in high resolution. So we could re-identify every license plate of every car, not just our cars, but the cars as a validation data set. We held a press conference with Randy Iwasaki, who was the deputy director of Caltrans at the time, Bob Iannucci, who was the CTO of Nokia. And while we were running that experiment on that stretch of freeway, we were showing to the press a live feed of the freeway traffic reconstruction exclusively from the phone. So no loop detector data, phone only. This is probably the first time in the history of smartphone that this was done live. I mean, it was just for a contained experiment, 10 hours for 10 miles of freeway. And so the press was very excited until at 10:30 in the morning, there was this big patch of red on the screen. The guy points a finger where we were at the time with the experiment. And people could watch the freeway. They wouldn't believe that 2 miles north there was this gigantic slowdown. So people started to debate whether the system was actually working. That woman at the time used to work at Traffic.com, and what you see her doing on the picture is she's actually calling the headquarters of Traffic.com. It disappeared since now it became part of Nokia, and asked for a traffic report to check on what we were doing. So this is probably the time when the whole team started to freak out and assume that the algorithm had diverged or started producing really crappy results. It turned out there was a 5-car pileup accident, and we caught it actually much faster than the CHP, which was there. And we figured this out because 5 minutes later, all their pagers, and you probably don't even know what a pager is anymore now, but all their pagers started beeping, which is they get an automated report every time there's an accident. So it turns out that that system worked extremely well, and that was good. And of course, the rumor then, it's a true rumor that some people asked me whether we had created the accident on purpose to demonstrate this. I freaked out by that question, and my standard answer to them has always been that that rumor came from Stanford. So we built that system 3 times. I mean, the notion in software engineering is you build it 1 time, you build it a 2nd time, it's still wrong, and the 3rd time, hopefully, it'll be better. So we built that system several times, and at the end of a couple-month period, we ended up having a nice set of feeds that not only took GPS, but also all kinds of other sensors, put it into filters, models, estimation, and was able to produce what was a first instantiation of a traffic monitoring system relying on smartphones. This is an example of what the data looked like. This is about 0.5% of the data we're using. We were never really able to show personal data for confidentiality reasons. So we showed a similar feed we were using, which is all the yellow cabs of San Francisco. And it's amazing if you just overlay the data over the period of 1 day, you can see a lot of the details of traffic in the map. I might be even able to show, I'm not sure if this is going to work. This is my daughter. I'm going to try to show you one movie. This is what it looks like. So this is kind of an inverted Pac-Man display. Each of the red dots is one of the taxi, and every minute it leaves a GPS point behind. And that's the kind of data you're looking at. And that's roughly, at the time, there was about 0.5% of the data we were getting. So you can get a sense of the scale at which we were dealing with here. So this was the beginning of a much bigger project, which finally led to prototype system that now has a lot of descendants in various companies and startups. Now, I want to talk for a couple of minutes about 3 typical problems you encounter when you build a system like this. The first one is privacy. The second one is the noise of the data. And the third one is what algorithms you run under the hood to make it work. I'll stay at a very general level, and then I'll move to the next part, which is really deeper and shows what we're doing now. So one of the issues with gathering GPS data at the time was the notion of privacy. This was probably the first movie we ever shot, or the first graph we ever shot of a student just driving through Berkeley. And we were showing this at the time, saying, look, with your phone, we can figure out all the traffic lights, including your traffic lights violations. We can also figure out where you live, and we can figure out the speed violations on the freeway. And we were just showing this to show that we're entering a new era of privacy where people might not want to disclose these things. And the main difficulty with this is that today, with your phone, you're sharing data with at least 3 or 4 companies, probably without knowing it, probably even without wanting it, every couple seconds. And with that, you're sharing a lot of information. In 2007, we thought that would be important, and we thought that would be a problem. It turns out that many years later, with Facebook, Twitter, and many of the other social networks, people seem to have forgotten about privacy and are very happy to share everything they have. So the architecture we built at the time was not really used for traffic monitoring. You probably all clicked on yes, 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 yes when you downloaded any app, and that means you're sending that data without really caring about it. That architecture I'm going to show is probably going to have a huge impact on tolling, because when tolling is done, it will be done by government agencies, and government agencies cannot be as loose as some of the private sector companies in terms of privacy. It's just they have different standards. And so what we created at the time, which we thought would be very helpful for the private sector, ended up not very helpful, is an architecture which was patented in 2007 called the virtual trip line. And the notion would be that you basically do not want to transmit your position every couple seconds, but if you only probabilistically send it upon crossing some specific landmarks, that could produce enough information to reconstruct traffic, yet protect your privacy. So the notion would be, OK, there's these landmarks which are embedded in the map. You don't see it because it's all in the map, but it's a hidden layer on the phone. And every time your phone is going to cross these landmarks, it's going to probabilistically send an update saying, hey, I'm a phone. That's the time, and that's my speed. And that would be enough to reconstruct traffic. So we built that architecture. The patent was finally accepted. It's currently owned by Nokia. And that paradigm became the virtual trip line paradigm. Yes? I am a phone, and there's a proxy ID which will be changed every time you change the landmark, which means they cannot track you. There's no way to know it was the same phone. And that's key, because that's this front end that doesn't go back end, because as soon as it goes back end, then you can track. And Microsoft showed very early on that even if you anonymize the trajectory, if you correlate with 3 other records, you can, with 90% chance, reestablish the identity of the person. So we did not want that to happen. And so that's why this probabilistic sampling was very essential to that architecture. So that architecture worked really well in practice. And our job as traffic engineers was to make sure that we can make it work with GPS data. It turned out that I think today completely useless to traffic engineering, because, at least as far as traffic information is concerned, because privacy, we could say, has been pretty much trashed. But when tolling through mobile devices emerges, and we see it happening with ERP2 in Singapore already, then I think that will become very important, because the government cannot afford to do what Google did or what Apple did or all these mobile companies did. It just won't work with, I think, with a lot of legislations in place. Now, dealing with GPS data is difficult, and that's mostly because of the noise. So to illustrate this is another example of a taxi in San Francisco. And if I'm following the tracks of a taxi sampling every 30 seconds, I could think that a simple algorithm to do map matching and project the data on the graph would be enough. Sometimes you go wrong because, OK, this is closer to the street, so it looks like the taxi is doing this, when in fact it's going straight. OK, that is a problem. But sometimes you really have some very strange things, like this taxi is here at time 9, and it seems to be behind at time 10. Why? Because the guy is probably stopped at the traffic light, and because of the noise error, it looks like it's actually behind where it was before. But if you take any typical path-finding algorithm, it will assume the taxi is around the block, which is completely wrong. So I'm showing this as one of the 10 typical problems you encounter when you deal with GPS data that you have to deal with. So our second job was to create machine learning algorithms that can transform noisy data, such as the GPS data we get, into some form of nowcast and forecast of traffic using combined map matching and pathfinding algorithms. And that's the second contribution of this whole couple of years of research, and not just our group, but a lot of groups in other universities worked on this. And I think one can realistically say that this field is very mature now. I think over the last decade, we have seen a lot of algorithms emerge and be able to do this. But that was obviously a very open problem back in 2008. The last problem I want to talk a little bit more in detail is the data assimilation problem, which is essentially what runs below the hood of any app that you're running that is producing traffic information. Every time you're turning on your phone and looking at either INRIX or Apple or Google or any other of these traffic information providers, there's going to have some algorithm of that same form that runs there. And I'm going to just give a very short preview of what that looks like. So the problem of reconstruction of traffic from sampled data is fairly easy to explain conceptually. You have some kind of a flow and a subset of the particles sending some Lagrangian measurements, which are basically sample trajectory around the flow. And the job of a traffic engineer is to reconstruct along the spatial coordinate over time the history of that flow, and that will give you nowcast information now. And if you're able to forecast using models like Michael Zhang's models or the cell transformation models or so other models, then you can even predict what the traffic will be in the future. So that's essentially the summary of what these models are. Of course, in practice, the math is far from being trivial. Typically, what you would use is conservation equations in which you describe the evolution of a density of vehicles throughout a stretch of freeways as a conservation equation. It's a first-order hyperbolic PDE called the Lytle-White-Richard PDE. And I think you probably have all taken an introduction to transportation engineering class, so you've seen a fundamental diagram in which you can relate the flow of vehicle to the density. The more people on the freeway, the more flow, until the density gets really high and then the flow goes down. So these are phenomenological models that go back to 1935. I think the first model was by Greenshields in Ohio in 1935, and there have been dozens of models since. And then you can discretize using a Godunov scheme, also very classical. That goes back to 1957, the first discretization of this PDE by solving Riemann problems. And that gives you an evolution equation for densities, saying the density at time n+1 at location I is whatever it was there, plus some term corresponding to the mass conservation. This is very, very simple numerical analysis equations to discretize the PDE. And then the question is, OK, now that you have these equations, you have multiple ways to do this. You could either work with density or work with velocity. And you could either work with discrete models or discrete velocity models. And so there are a lot of subtleties that you have to deal with. But if you end up working here, which was one of the contributions we make back in 2008, then the beauty of this is that, and that's a very subtle distinction, you can reconstruct velocity from measurements without reconstructing density. And that's very important, because back in 2008, if you were assuming that you could only measure 2% of traffic, 2% of traffic is not enough to tell you how many people are using the freeway, but that might be enough to tell you how fast they're going. In 2015, it's different, because if you're Google, and Google doesn't share their data, but inside of Google, they probably have already more than 50 or 60% of traffic. That's because more of half the population is carrying an Android phone. So now it's very different. But if you're just looking for velocity, that's a key question. And even if Google and Apple might have it, Google and Apple are not sharing it with the government agencies. So that is still probably the road you would want to take to provide velocity estimates. So the notion is that now you're discretizing the freeway into cells in which you have values of velocity at a given time. And then you find the proper evolution equation for the velocity, which is nothing else than the translation of the discretization of the PDE into the velocity domain. Also explicit. The problem is it's very nonlinear and also non-smooth. So it doesn't lend itself very well to filtering techniques you would typically use to do an estimate with noisy data. The beauty of this is that you have a measurement equation which relates the speed in a given cell to the state in a linear manner. And that's because if you're a phone traveling on the freeway, you can measure the speed of the phone. You cannot measure, at least to this day, the density of vehicles around the phone. And so having a linear measurement equation may give us a lot of nice property to use statistical filtering techniques to do that estimate. The algorithm we used at the time, which is still, I think, used by a lot of companies that have taken this and made it into their main product, is a simple ensemble Kalman filter, which is using this velocity equation. So it's basically the history of the velocity plus some noise, and then providing some simple measurement update techniques based on Monte Carlo simulations to update the estimate of the state. So these techniques are the techniques standardly used in meteorology. So this is really what the weather forecast is using. When you're watching the weather forecast on TV, that's the mechanism they're using to forecast the weather. And so we were the first to use that forecast mechanism for speed on the freeway with Lagrangian measurements. And that was the contribution at the time. So there's equations that can back this up. I'm going to show what it looks like in practice. This is what 2% of traffic looks like if 2% of you were willing to transmit your data to a single entity. You could basically follow along the freeway over time the trajectory of 2% of traffic, say every couple seconds. This is the accident I was talking about. So you can see people going fast in blue, about 65 miles an hour, and then slow, and then fast again. So Google today probably has 40 times more data, just to set this in the current context. Again, it doesn't mean Caltrans has that data. It just means Google has it internally. It doesn't mean they're giving it away. Now, if we talk about privacy, that's the data we have. We basically have the same data, except now it's a subset, because you remember, you only give your data probabilistically when you cross the landmines. So now the question is, can you do the same job with that data, which was the second big question we were asking in 2008. So the answer is yes, you can, and that's the result, for example, for that day of the reconstruction of the data using this statistical filtering technique. And we were very happy because we could show that not only it would work with 2% of the people, but it would also work if you got rid of 99% of their data, because basically they're not giving data unless they're crossing something, and even then they don't give it all the time. So I think that has been proven very effective, and I think when the era of tolling comes, and when the era of mobile tolling comes, which it will come within the next 5 years probably in Singapore, and maybe it will take longer for the US, I think that will become very helpful because the architecture is there. And I'm sure that whoever owns the patent then, assuming it will be sold and resold between different companies, will be very happy. Back in the days, people asked us, well, how are you benchmarking this? And so the movie I used to show at the time, which is becoming irrelevant now, is a comparison to what Google was producing way back when. So what you see here is I'm just going to pause it to explain. This is back in 2008. This is what Google looked like, 2009, sorry. And this is what our interface looked like. And what we were showing at the time is it was before Google made the transition to using that data into their main system, is that with that data, you could probably predict things about 15 minutes faster than would appear from the dedicated sensing infrastructure. So you'll see an accident happening here. You see it happening now. The frame is about 30 seconds, so things are running 30 times accelerated. And then the accident is happening now, and it's still not showing on the Google feed at the time. The benefit of that was to show that you could really have a much, much faster pipeline, in addition to the fact that the data was a lot more precise with respect to other sources of data. So to finish that part of the talk, we had a fairly nice run. I mean, it started in 2008, and then over the years, what we did is we kept improving the system and added a lot more algorithms to it and added routing to it and many other things. And I think what's really nice is that if you look at all the companies in the ecosystem, more or less all of them at least either joined forces or hired our students or interns or subsidized projects. And I mean, it's fair to say that even though it started with Nokia and Navteq, who then took the architecture and re-implemented it internally, other companies like Telenav also did it by hiring our students. And Apple, Google, and Microsoft also hired our students. Of course, once they cross the border, we don't really know what happens with the technology and the algorithm. But there's a lot of evidence when we talk with them that these things are now really prevalent. And certainly the algorithm that run in the hood are very, very much close to what we did. So now the real question is, it's 2015. Traffic information is mature. Every company has it. Probably no company makes money out of it. I think it's very hard to make money out of traffic information. So there are some exceptions like INRIX who have very specific business models. It's more of a downer in the sense that if you're a company like a major internet access provider or information company, it hurts you to not having a mapping system which has traffic information, but traffic information is hard to make money of. Now the next question is, what about traffic management? Take 5 years from now, we might be in a situation where the government is losing control of traffic management. Why? Because if you look about the infrastructure, how do government agencies manage traffic today? They have traffic light, they have metering, they have changeable message signs, maybe they'll have variable speed limits, and these are pretty much the only way a government agency can enforce traffic. Tolling, I guess you can change tolling. But where do you get your information? From Google, from Apple, from all these companies. So very soon you might be in a situation where the government start to lose control because people will just do what the apps are telling them to do. So the question we should be asking ourselves now is, first, how to model that, and then second, what to do with these models. So today I'm going to show how to model that, and then I think what to do with it, that's still something which is open, but very interesting problem. So now we assume that everybody has this, because you all have this on your phone. And in addition to having this, you also have guidance. Google says you should use this bridge. Apple says you should use that tunnel, and so on. Now, not everybody has apps. Not everybody uses apps. So the notion is, what do we do when one portion of the population is going to do as told by the apps they're running, and the other population is going to do what they do usually, which is user equilibrium, and do things which are selfish, best for them. So I'm going to illustrate that on a very academic problem, which is a simple routing problem. I'm just going to take a parallel network because it's easier. And the notion is you have people going from one origin to one destination, and they can take n routes. There's an overall cost to society, which is the total travel time. That's one possible metric, TCT. So think about going to San Francisco to San Jose, and think idealistically you had 4 routes. So 280, 101, 880. OK, that's fair. You could use the 3, and maybe the 580, 680 is a bit far-fetched. But OK, say you have 4 routes. There's many urban cities where you have more than 4 routes. OK, so the problem I'd like to talk about is, what if a portion of the population could be controlled? You give them incentives. You give them something. Get them out of the car to get them into the transit system, while the rest of the population is just doing their usual thing. That's the question. Why? Again, because in a couple of years, it might very well be that with all the apps we're using, whether these are routing information, transit information, traffic information, bidding on stuff, personal trackers, all kinds of ways, and many of these apps, we might really be in a situation where it's actually the private sector which is driving the way traffic is managed at a local level in cities. That is called the Nash-Stackelberg games. There's a very simple concept in economics called Nash-Stackelberg. And in Nash-Stackelberg games, what you have is you have a portion of the population, we'll call them the good guys, who are doing what you tell them to do. So for example, OK, if I give someone a lottery ticket, like Balaji Prabhakar is doing at Stanford, they might just decide to not drive on that day. If I give them a cappuccino reward, free cappuccino if you exit the freeway now to go to Starbucks, OK, while you're tired, it might be a good way to break, and if you get a free cappuccino, it's even better. So let's assume there is a way, or tolling, which is kind of the repressive way. OK, you say, OK, great, we're going to just hijack the toll to super high level on the freeway. Then clearly you want to get off the freeway because you cannot afford to pay the toll every day. So some way to get a portion of the population to do something. Given that most likely the 95% remaining will just not do anything about it, because cappuccino does not get me out of the freeway. People like John Walker at Berkeley are very good at computing the value of time, or the value of green, or the value of something. So there's a portion that is just immune to that will just not react. They'll just do their selfish thing. So that framework is called a Nash-Stackelberg game. It's called Stackelberg because the Stackelberg leaders in economics are basically the ones that are going to be compliant. And the Nash players are going to do the typical user equilibrium they do regardless of what the others do. There's a proportion alpha doing the good thing, and there's a proportion 1 minus alpha doing what they usually do. Now, this concept is fairly used in internet routing because internet routing protocols and people like, for example, at Stanford, like Tim Roughgarden, have studied quite a lot how, what should you be giving to the good guys so that the overall social optimal resulting from the combination of the good guys and the bad guys is as good as possible for society. In the context of traffic, it's never really been studied in that context because the difficulty is you still have to deal with this. Now, this is what you learn in Traffic 101, which says that, you have, everything is linear until traffic jams start to happen, and then things are troublesome. Routing packets on the internet is very different than routing cars on the freeway. So the notion is, could you extend that theory to a type of system which is behaving like this concave flux function? I'm just going to deal with that in a static setting. If you make it time varying, it's even harder, and I think that's still an open problem today. So think about what happens to the travel time of a packet on the internet. So you've probably all been in a hotel where the wireless is pretty crappy, and it takes forever to download something. And the reason why it takes forever to download something is as long as you're below the bandwidth where you've kind of free flow, okay, the download rate is the same. And as soon as you start to be bandwidth limited, and basically the latency of packets routing is convex, so it looks like this. And it takes, at some point it might take forever for you to download the next packet because the network is completely congested. So this, just go to a place with poor Wi-Fi, you can experience this every day. In the context of traffic, it's different because in the context of traffic, what happens is that your travel time is roughly going to be the same. So if I go from Berkeley to Davis, until the traffic is congested, whether there's one guy on the freeway with me or a couple hundreds with me, as long as it's uncongested, my travel time is roughly the same. I'm a French driver. I'm aggressive. I drive slightly above the speed limit. So the travel time is the same. And then, as you keep increasing people, the flux starts to decrease, but your travel time increases. So remember, density increases. The more people, the more dense. But flux decreases because the freeway is less efficient. So that's a strange function. Now it's multi-valued. If you look at a given flux, okay, 1,000 car per lane per hour, you might have two values, uncongested or congested. So this routing problem that comes in the context of internet routing, in the context of traffic, has an interesting form where now the latency function, how much does it cost you, depends on the flux in this nonlinear and non-univalued manner. Okay, make a couple of assumptions on the network, which are not very relevant to talk about now. Now the question is, how do you do that analysis on these types of network? So first, let's look at what a Nash equilibrium is in that context. So say you're going from here to Berkeley. You could use 80 or you could use 680, and let's say there's a third route. So if you use the fastest at free flow, 80, you'll have a given travel time, say 1 hour and 5 minutes, roughly. If you use the next fastest, so 680, you probably have a travel time of 1 hour, 15 minutes. And then if you take the next one, I don't know, maybe you go through Santa Rosa, now this is going to be 1 hour and 30 minutes. And if you go through even crazier route, it might be even longer. And that's all for free flow. And then if you start to have congestion, of course, the travel times gets worse. What is the notion of a Nash equilibrium on this type of network? A Nash equilibrium in an equilibrium in which you don't have an incentive to change because any change incurs a penalty. It's a very simple concept in economics. That means that whatever the current travel time is, everybody is equal. So whether you're going through Santa Rosa or through 80 or through 680, you incur the same travel time because it's a Nash equilibrium. So that means Santa Rosa, you'll be free flow all the time because nobody goes through Santa Rosa to go to Berkeley. But 680, you'd be somewhat congested, and 80, you'd be really, really congested. You're way above the travel time on 80. Okay, that's the notion of a Nash equilibrium. So Nash equilibria in these types of latency function have a very nice property, is that you can compute them actually polynomially. That means in a polynomial time with respect to the number of possible routes, using that nice property. That's something which is not true in internet routing. And so that's nice because, ironically, even though the latency function is much harder in traffic, the problem is much easier to solve than in internet routing. And the way you construct these are quite easy. Basically, if you try to do what's optimal for society, what you should do is you should fill your first link. And when it gets too crowded, like this, then technically you should start filling the next one. But because people are selfish, that's not what they're doing. what they're going to do instead is they're going to stay on the route they think is the best while other takes the other route, and that is inefficiency. So there's a concept of price of anarchy, and that explains the price of anarchy in the context of traffic. It's saying that because people are doing the selfish thing, the efficiency of the network disappears. So there's a nice property that shows that you can enumerate these equilibria in a time which is polynomial in a number of links. And that's what makes the problem much easier to solve in the context of traffic than in the context of internet routing. And there is also another property which is very nice, which says that at a Nash equilibrium, you have at most one link which is uncongested. And that's basically saying you congest all the links except the last one. And when you have congested the last one, then you move to the next link. That means opening a new road, which, again, will be uncongested until it gets maxed out. So once you have this nice property, then you can start asking the question about Stackelberg routing, which is that's if people are fully selfish. So it's a society in which everybody's doing best for themselves and is not really taking any incentive. Now, say I'm Waze, or I'm a company, and I have a partnership with Starbucks and with Macy's, and I can say to any user in my network that if they do whatever I tell them, even though it might not be optimum for their routing, they'll get a benefit by being given a coupon or some amount of money. So now you're in a situation where you can control a portion of the population. And what that means is that when you're computing your latency, you're going to compute the latency of the combined flow of the people who do what you're telling them to do, S, and combined with the other part of the population, T of S, which are basically doing as they usually do. And then the question is, what do you tell them to do, given that the other guys are going to be selfish, so that overall, given you can only control 5% of the population, the overall outcome is as good as possible, as close as possible to societal optimum. That's called a Stackelberg strategy, or Stackelberg optimum. And what it says is that you're looking at the combined cost of the good guys and the bad guys. And that's, of course, a proportion of the how many good guys, how many bad guys. And among all the possible solutions, you're looking for the best. That's the optimum Nash-Stackelberg solution to that problem. The algorithm I've shown before on how to stack things actually works with that framework and provides a very good way to compute that optimal strategy, which is a Stackelberg strategy. The way to show this is that, if everybody was selfish, or if a given proportion of solution was selfish, then everybody would be equal. Some people might be on a longer route, but with the same payoff as a shorter route with slower traffic. That's what this is saying. That's where the inefficiency is coming from. So now, if you try to figure out what do we do with the good guys, what should we ask the good guys to do so that the bad guys don't suffer extra penalty, because that's where the social system becomes inefficient, then what you should be doing is you should tell to the good guys to keep filling that route until that route gets fully congested. I apologize, this should be kind of a blue line here, but it doesn't display well on the projector. And then instead of being inefficient, you should tell the good guys to take the next route. The next route is much longer. That means now the good guy has to drive an extra 15 minutes, but he gets paid for it. So that's the reward. And if you keep filling the routes this way, then you can prove that what you incur is something which is as optimal as it can be, given that you can only control 5% of the population. And these are basically the compliant users. They are using the routes you tell them to use to decongest where people are selfishly going, and then you let the selfish people fill the rest selfishly. So that's a static model. There's a lot of limitation to that model. And also what it doesn't consider is the fact that people learn over time. So that is not stable. You can make it work a couple times, but over time it will not be stable. And so the notion of online learning and how people react to it over time obviously is an open problem on these type of equations that are still not solved to our knowledge. So, but just in that static case, which is really a first step towards what can be done, you can prove that that strategy is optimum. And it's a very nice counterpart to what's happening in the internet literature, because it provides the same guarantees as in the packet routing literature, but the benefit is that, ironically, because our cost functions are so much more complicated than the internet literature, the problem is much easier. And there's some robustness results that can be associated with it, and I'm just not going to go through them. So with that, you can compute what's called the price of stability, the value of altruism, or there's another notion in economics called the price of anarchy, which is basically the ratio of what would happen. So for example, if you could compare what would happen if a proportion of alpha is compliant over the situation where nobody's compliant, so it's like everybody's selfish, and that's called the value of altruism. So with these models, you, for example, in going back to this simple case of San Francisco and San Jose, you can compute that. It's a very idealized case, of course. There's a lot of steps to go before we can make it into a real concept that works in practice. But you can show that, for example, if you have more and more demand, the price of stability gets higher. And of course, the less compliant user, the worse the situation will. So you can compute these, and these jumps that you see in this value function correspond to every time you have a new road you use, then you have a jump. So these are a very nice concept to compute in economics. So I want to finish the talk by kind of expanding a little bit to show where this is going. Obviously, there's still ways to go before this becomes reality. But in places like Singapore, with the ERP2 system, it is very likely that these concepts might come to fruition early because you have already evidence that these models work well. So I think what the future gives us in terms of where this is going is monitoring is going to continue growing. I think with satellites, now we have ways to do a lot of forecast. A couple years ago, the German DLR reprogrammed the satellite to orbit around California so we could gather traffic information from satellites and show that this would provide good things. We also work with the Department of Defense with flying planes over some unnamed cities to see if we could reconstruct traffic in places where you don't have any infrastructure and you're interested in tracking specific people of interest. So the sources of data, both for demand and for estimation, will grow, and that will just be in fusion with a lot of other things that we see emerging. What that means is that also it becomes possible to predict things like noise level. We're seeing the first noise maps emerge live from this data. I mean, back a couple of years ago, when you wanted to predict noise in the city of San Francisco, you would average all the counts of vehicles throughout the year, throughout specific places of the city, which is completely irrelevant for noise because you would noise at 2 a.m. and at 2 p.m. are absolutely not the same. Now you could do this live. Emissions is another thing. From our models, we can already predict emissions with very simple models like CalINE, constructed by Caltrans, and other atmospheric science models. And this is what we were showing a couple years ago. There's now startups coming out of Berkeley with people who have air quality models, air quality sensors that hook up directly to your phone, not through the USB anymore, and that can validate this. So already with that traffic monitoring, I think we're already seeing a lot of different layers you can bring to a map that can be predicted fairly accurately on an hour-by-hour basis. The things I'm particularly excited about is the notion that we're still very far from operationalizing this into traffic management. And that's because while Google might have all this data, government agencies don't. So one thing we did a couple years ago was we did the first procurement of GPS data by the state of California as a proof of concept that the state could acquire this data. And this is just the beginning because I think the market is not ready and the market is not there yet. But just the procedure, it was actually very exciting. So Berkeley, we put together the RFP, we administered the bids, and basically selected the winners. And typically, when you buy GPS data, there's a lot of questions you have to ask, right? I mean, if you buy it for planning, you really don't care whether it's live or not because you will use it on a yearly basis. But if you buy it for traffic operations, data that is more than 5 minutes old is almost useless. So typically, this is an example of a data feed that shows that most of the data you're getting more than 300 seconds after it's collected. That means it's more than 5 minutes old. That means most likely useless for traffic information because you don't want to know, I mean, if it takes 5 minutes to get it and another 5 minutes to process, you don't want to know traffic 10 minutes ago. You want to know traffic now. Or if a vendor tells you, oh, no problem, we're going to give you 7,000 data points an hour for this location, but on average. But if you look and all the points are actually during the night and you have nothing during the day, why? Because it's a trucking company and they have all their vehicles going at night, that's also useless for traffic information. So there's all these criteria and metrics that we built to try to figure out how you price GPS data. Do you buy it by the kilo? Do you buy it by the pound? And how much is a pound of GPS data? And how do you define a pound of good GPS data? And so all these metrics we built, and that enabled us to do procurement. The next stage is management, how you put this into managing traffic. One of the pilots that we're very excited about now, which we do through the Division of Operations at Caltrans, is a 210 pilot. And what we're doing there is we're merging the control infrastructure, such as this changeable message signs, parking, HOV lanes, ramp metering, and arterial traffic, to try to create a decision support system that will enable us to implement these concepts. So if you're diverting 2% of traffic on the arterial, you have no way a priori, sure, it's going to be good for the freeway, especially if you do this in response to an accident, but this might completely mess up the traffic on an arterial. So having joint models that can assess whether that's a good thing or not, whether that's sustainable or not, that's still something which is not very well operationalized. So one of the pilots we're working on, the 210 pilot, hopefully will bring to fruition a kind of an integration of these models and see how, if the state at some point was able to deploy apps or incentives like they do in other countries to get people to change their routes, how do you do it in a way that is a good thing for the efficiency of the freeway? So this is the area in which we're working in Southern California. These are the number of, every dot here is one of the control points we will have access to. So these are traffic lights with potentially 170 or 2070 controllers. And the work we're doing has to do with how you model this and how you control this. Not only a technological problem, but it's also an institutional problem. And that's mostly because all of these different control mechanisms are under different jurisdictions. So if you do the 210 corridor, if you just take half of the corridor, you already have 4 cities, Pasadena, Duarte, Monrovia, and Arcadia. So getting a coordination plan so that all these agencies can work together with the state is not an easy thing. I mean, mostly because the goals might be conflicting. I mean, some might want more freeway traffic, some might want more arterial traffic. And at the core of it is an architecture that we're building that can support this. The very first part of the talk, that's the yellow box. So all the things I talked about for traffic estimation and GPS smartphones, that's this box. And there's a lot of other boxes that need to be built to support the different functionality of the system. I don't have time to talk about this, but integration of social network data like Waze. We used to work a lot with Waze before they were acquired by Google. Understanding how their posting affect traffic. This is kind of a word graph of what the words people post on Waze when they travel. We had to clean a lot of words because they wouldn't be proper to show here. People curse a lot about traffic to express their anger, but you can see a lot of different things here. So in the future, things we're doing is we're working a lot on energy. This is the Create building in Singapore. We have instrumented a lot of this infrastructure, and we're coming up with a smart technology to monitor energy consumption from devices. There's a lot of interactions with traffic in terms of forecasting how energy is spent in buildings if you know traffic. Other things we did, and we're still working on, is monitoring earthquakes with smartphones. All of you have a smartphone, and most of the time it's at rest on your table or when you charge it. So we were one of the first groups to deploy an app that monitors earthquakes using smartphones when they're at rest. We tested it in various facilities. And then finally, things we do closer to here is, I guess we've seen a driving phone, a shaking phone, that's a swimming phone. We have an army of water robots, which we usually deploy in the Sacramento Delta. So in the very same way that when the phone is in your car and it's basically monitoring traffic, I mean, when it's in the water, it's monitoring water. So the idea is you can construct a map of currents at various scales depending on how you show it. So we mostly try this in the swimming pool to start with because it's a bit hard. But so here what they do is these guys have motors. They have a smartphone inside, and what they do is they monitor the currents of water when they're not propelling, like this guy is kind of static. And they all transmit their data wirelessly to a single system, just like the phones on the freeway, to provide an estimate of the currents in real time. So we have to do a lot of testing in the swimming pools before these guys are ready to go. And it's kind of fun things to do, especially in California. And so typically what the students do then is we deploy them in the field. This is the last slide I have for today. That's John. This is so we go in the Sacramento Delta in Walnut Grove, not too far from here. and then we just dump a lot of them in water. And then once they're spread out, they can start to stream their measurements. This is accelerated because watching traffic is boring. Watching water is also boring, so we have to make the movie faster. But these things can readjust themselves in the water to get measurements where we need them. And then you have these gigantic models. So this is kind of a model of water, just like you do a model of traffic. And then the red dots here correspond to the places where you get measurements from. So at the end, the philosophy is always the same. You have mobile sensors. They monitor feature which is distributed. You try to reconstruct it, and maybe one day you try to control it. So that's pretty much all I have for today. I can answer a couple questions if you have questions. And otherwise, again, thank you, Dan, for the invitation. Yeah. Thank you. Travel demand. So say, for example, ODs? Okay, yeah, so I didn't show it today, but we have access to all of AT&T's data for California. And one thing we're doing right now, and we've been working on this now for 9 months, is user equilibrium inference and OD inference from cell tower records. So there's a main difference between GPS data gives you a position for a very small subset of users. But if you have access to a major provider like AT&T, now you have a very high percentage of the population. I cannot tell you how many. It's confidential. They probably don't even tell me the real number. But say nominally more than 30%. So if you have 40% of people's CDRs, which is roughly the cell tower they're talking to, you can fairly easily infer work, home, and somehow commute patterns. And so that's the type of thing we're doing. So you can view this as an inference problem onto the Nash equilibrium. You get people's origin and destination, and you're trying to figure out the most likely Nash equilibrium given the data you have. So we'll have a paper this summer at the ISSST on this. It turns out that for ODs, I think cell tower records are awesome. They're a phenomenal source of data. For routing and user equilibrium inference, maybe not. Because if you look at cell tower records, for example, if I'm driving here to Berkeley, you will see a lot of zigzags around the freeway because of the cells being very big. So it's a very good tool for OD estimation. But for routing and inference, it's not clear that it's there yet. Singapore, yeah. Singapore. Maybe later as well, yeah.
That's really a VMT.
So in a sense, it's funny because I don't think in Singapore that the cost function has been determined. The technology is there and the process of tolling is there, but the cost I'm not aware of. So I can answer the reverse of your question, but I don't know the cost. So let me be a bit more specific. In Singapore, in I think like 2 or 3 years from now, it will be mandated that every vehicle carries a box which has a GPS that determines uniquely on which road you are, which means Singapore will be able to toll road by road, link by link, your journey. So that technology is there. It's called ERP2. It's an improvement with respect to ERP1. ERP1 is just gantry-based for the major freeways. So we already know that the plan is to toll link by link, road by road. What's unclear to me, but that's also because I don't think it's been determined, is, what will they toll? Will they toll? My sense is they will toll by distance, because I think that would be the right thing to do. And then they will weight that by link. So this link is really bad. You don't want people on Orchard because it's congested 24/7. You want people on subsidiary roads. But I don't think that they have clearly established what the tolling scheme will be. The only thing we know, to my knowledge, but again, it has to be checked, and the bids for that just went in 5 weeks ago, so I think it's not, there's 4 bidders already who have bid on how to build that and how to price that. The only thing I know is that they will publish the fares a couple days in advance, just out of fairness. So that's what's been agreed upon, but they have not said how they will price. So the notion of publishing the fares ahead of time is because obviously you don't want to be in a case like with Uber a couple of years ago, or actually last Christmas there were these crazy fares in New York. You heard about this. People assume that the fare will be the same, and suddenly it's not the same. And since you don't check, then you get priced a crazy amount. So with Singapore, they will publish the fares ahead of time so that you know what street will be priced how much ahead of time. But I've not looked carefully, and I don't know if they have actually established the schemes. My sense is that it should be a fairly simple scheme in which, based on simple concepts like user equilibrium, they should figure out what are the bottlenecks and just price the bottlenecks higher to reestablish traffic, which then goes back exactly to the framework of changing the latency function in the Nash equilibrium. But I think that's still an open question. There's a couple of teams in Singapore who work on this. The Colab of IBM is working on that pricing, and I believe they work with NTU. But I don't know exactly how far they've gone in terms of the pricing. Does that answer the question? Yeah, it's crazy. I mean, I think this is opening a new era of equity, fairness, optimality. Yeah. So then how you create a pricing scheme that people don't game the system, right? Because if you know that it's always going to be expensive at that location, then people will start to change their routes. And then if you see cyclic patterns, people will game it. There's actually a whole body of literature on online learning that shows, okay, take a simple problem. If all of us commute from this part of campus to Sacramento, and if we all exchanged our information at the end of the day, so how much did it take you? 5 minutes. How much did it take you? 7 minutes. And we share our itineraries. If we exchange that information every day, and we readjust our itineraries based on this, then there's a simple theorem that shows that that converges to a Nash equilibrium. So you're right, it's not optimal. Because basically, we're exchanging information in a way that we're all converging to something non-optimal. So I think there's huge problems associated on how you design a proper pricing scheme to achieve the outcome desired for whatever I don't know, probably a city wants to decongest some places. So how you find the right congestion scheme. I don't know that this has been solved yet. We talk with the California Transportation Commission. We're not directly involved. VMT. Yeah, oh, sorry. So we're not. Yeah. So the question is whether we're involved with the California Transportation Commission on the VMT pricing scheme. We're part of the conversations, like we're part of the groups that meets on a bi-weekly basis. But I don't. And there's the pilot coming. But I don't know that the pilot has been awarded yet. So at the present time, we're not involved in the pilot, and we're not involved in the evaluation of the pilot. I think the process is still in a very, it's the beginning of the process. But I mean, clearly, the same questions that we see in Singapore will be raised in California, because I think that's a fairly common problem, and the pricing is very unclear. The one thing which I'm very excited about, going back to the very beginning of the talk, is this. Because if you think about how you create an architecture in California that can support it, I think it would be very problematic for people to accept to be tracked from their homes to their work location for being told. I mean, I think there's a cultural gap in the U.S., and that's normal, right? I mean, sharing data is very sensitive. So an architecture like this, where you toll at specific location without tracking people is, I think, essential in making that scheme acceptable from a social standpoint. It doesn't say anything about the pricing. It only says something about the architecture. I think the pricing is very complicated. I think we're just scratching, from my perspective, I think we're just scratching the surface now. Yeah. Okay, so the question for the since you don't have a Mac, is right now the paths are independent. It's like a parallel network. What if some of the portions of the road were shared? The results we have shown here, the analytical results we've shown here only hold for a parallel network with latency, which are in strictly increasing order, which is a technicality because you could cut roads in two. If the roads had a shared portion, you would have to decompose the network into some form of parallel network for the unshared version and some joint portion. I think all the analytical bounds we have are gone. I don't think you can solve this analytically. I think that you have to use some form of optimization through the Nash equilibrium. For that, you would probably use a Rosenthal potential, decrease it as a convex potential. But I don't think you can. I'm not aware of any analytical solution. So then you have to resort to numerical optimization. The Nash problem is still convex because of the Rosenthal function, so that's okay. The Nash-Stackelberg problem, I don't know. I think it might just be nonlinear, and I would be very surprised if it was convex. To my knowledge, that's an open problem. So there are a couple attempts that have been made. There's a paper by Zilokopoulos that shows that if you have a single destination and multiple origins, and you use a cell transmission model, which is the simplest traffic model you could use, the problem is convex. If you have a multi-commodity on a network with multiple origins, multiple destinations, again, I think, unfortunately, you're back in nonlinear land. And so I'm sure you can find some specific network topologies and some simple enough traffic models where you could probably extract a convex program out of it. But I think the general case is fully nonlinear. And there, unfortunately, I think you have to go back to heuristics. So clearly, there are limitations. There's no free lunch, right? I mean, the more complex the model, the harder the math is. This is very idealistic. And then for the real thing, you just have to use nonlinear solvers. Partnerships? That's happening already. I mean, how many of you use Google Maps? So, okay, everybody, all right? So that means all of us in this room are following guidance from a company. I mean, not to point Google, because, I mean, a lot of us use Apple, Telenav, Inrix, but what does that mean? That means that all of us are following guidance from companies. And, okay, so we've all worked with these companies. How many of the employees of these companies know what a user equilibrium is and what is a social optimum solution to a multi-commodity flow network problem? Very few. Why? Because the business plan of these companies is not aligned with that. If I'm a company and if I'm providing a routing scheme, so say I create my startup tomorrow and I try to create a router so that all of you use the buy-in router. My goal is to make money. How do I make money? By basically providing a routing service that has a revenue, for example, with partnerships, for example, hooking up with a social network, whatever you want. But that selfish routing has nothing to do with social optimum by nature. So even though you see claims that some companies are making traffic better by giving you better routes, as a user, you want the best travel time. You want your best outcome to the process. That's by definition a Nash equilibrium. We can see it happening already. In fact, if you look deep enough in the news and you search on Google, so put your favorite name company, and then try to add to it induced traffic jam. So I don't know. Let's say we have the Zorglub. I don't want to say a specific company. Obviously, this is recorded. So let's say we have the Zorglub company, which is providing a router. So search on Google Zorglub induced traffic jams, and then you will find a lot of articles of cities that are starting to rebel because they see now traffic jams in their cities, and they very highly suspect it's due to routers imposing extra traffic on them. This is an example of a city losing control over its traffic. Say there's an accident on I-80, and your favorite traffic app says you should go through Davis. Everybody's going to go through Davis because there's probably 10 or 20% of the freeway population which is using that. That means the city of Davis has completely lost control over its traffic. It's not able to control its demand anymore. And the only way you can do it is by maybe changing their traffic lights so that they limit the number, and then you can imagine the kind of problems it gets. So that's why I'm saying in the next 5 to 10 years, unless something is done, the public agencies are going to lose the ability to control traffic because traffic is controlled by something which is not in their jurisdiction. That's going to change a lot of things in the transportation landscape, just like it did for traffic information. I mean, just going back to this, 10 years ago, who would have thought that the best place to get traffic information was Google, when Google was just a search engine? I mean, everybody would go to 511 because that was the only way to get traffic information. Now it's the same with traffic management. That's game-changing. Hopefully for the good. Thank you.
It's not going to be. Less arguing and more just like people talking about situations. This works. Yeah, we'll see if it works out. Yeah, we've talked already. Yeah, we got readings pretty much figured out. Okay. Curiosity. Thank you.
Sorry, we have to chase you. We have another event. If you need a room, I can get a room. Still plenty of food if you want anything out there. Let me go ahead and
We just congregate people here.
way last time. Sorry, we had to chase you out.
His name will be the first one.
Yeah, that would be a better one. Problem is, we've got this under here, so I don't want to. We're gonna move this. Oh, okay. You're not going to use this? Okay.
Yeah, no. Listening to your concerns and listening to Dave's